In this video, we are going to put our counting techniques to work in what are called combinatorial proofs. So first, we're going to discuss what combinatorial proofs are. We're going to discuss how counting methods can be used to determine what are called identities. And then we're going to do a combinatorial proof. And then in the end, we're going to reflect on what makes a good combinatorial identity. All right, so to understand what combinatorial proofs, let's break it down. We have the word proofs in there, and all proofs is explaining why something is true. So you say something is true, and you give a convincing explanation of why it's true. So this often is done with words. Sometimes it's done with symbols, but it's just got to be communicated. And then there's the word combinatorial, and all that means is it has something to do with counting. So that's just all the stuff that we've been working on in this chapter, counting stuff. So a combinatorial proof is using counting methods to explain why something is true. And for our purposes, that something is usually going to be some kind of an equation, a special kind of an equation that we call an identity. All right, so here's how we tend to approach a combinatorial proof. So we identify a quantity to count. And what we do with that quantity when we want to count it is we count it in one way. Then we count the exact same quantity but in a different way. And since both methods are counting the same thing, that means they're literally the same number, which means we can set the two results equal to each other. And that gives us an equation that is true. So the resulting equation, when you set the things equal to each other, that's what you are proving. All right, so here's an example. We're going to identify a quantity. We're going to count it twice and get a weird-looking combinatorial identity that we would never expect to be true. So here's what it is. And actually, it's something that you've seen before. So this is the JoJo problem where they were ordering sandwiches and salads. So a menu offers M sandwiches and N salads. How many ways can you order both a sandwich and a salad? So we're going to count this in two ways. I'm guessing you know what the first counting method is. That's a perfect setup for the multiplicative principle. So we just multiply the choices of our sandwich with the choices of our salad, and we get M times N ways to order one sandwich and one salad. All right, so for the second counting method, we're going to do something a little bit different. So it's got to be different from the first method, because if it was the same as the first method, we just get M times N again. That would give us the equation M times N equals M times N, which, you know, is true, but, I mean, what's the point? I mean, that's the most boring equation that I've ever seen in my life, right? So we want something that's slightly more exciting. So what we're going to do is, instead of just multiplying the number of sandwiches with the number of salads, we're just going to put all the menu items together, the sandwiches and the salads together, and combine them so we have M plus N choices for the sandwiches or salad. Then what we're going to do is we're looking for pairs, right? We're going to put them in pairs any way that we feel like it. So we're going to choose two items from the entire menu. We don't care if they're sandwiches or salads, right? So we have M plus N items. We choose two of them. And there are M plus N, choose two ways to order them. Here's the deal. We have too many possible orders, right? Some of those M plus N choose two ways that we ordered are going to be two sandwiches. And we don't want two sandwiches. We want one sandwich, one salad. The other way we could have screwed it up is to, and that's M choose two. There are M choose two ways of doing that, right? The other way we could have screwed it up is to order two salads. And there are N choose two ways that we could have done that. So I just took all the menu items together, put them in pairs, and now there are M choose two of those pairs that are bad because they're two sandwiches. There are N choose two pairs that are bad because they're two salads. And what we want to do is take all the orders that we did, subtract out the orders that we don't want, and that will give us the orders that we do want. All right, so that is M plus N choose two. That's all the pairs. We're going to subtract out the ordering two sandwiches. We're going to subtract out the ways we can order two salads, and that gives us our result. So how many orders do we have? Well, on the one hand, we have M times N orders. On the other hand, we have m plus n choose 2 minus m choose 2 minus n choose 2. Since those are both counting the exact same thing, they are actually equal. So m times n equals m plus n choose 2 minus m choose 2 minus n choose 2. And that's pretty crazy, right? Because if I were to tell you that equation was true before, you would have thought I was nuts. And even now you may think I'm a little bit nuts. But think it through. It has to be true. They are literally counting the same thing. So here's the note. Whenever we decide on something that we want to count, there's usually one of the ways that we count that is normal. That m times n was just the natural way of counting the number of ways. And then there's one way that we count that is weird, right? We can't just count it normally twice because then we get a stupid equation, right? The only way we're going to get an interesting equation is if we count one in a normal way, or at most one in a normal way, and at least one of them in a weird way. So all I say is when you're doing these combinatorial proofs, you should be prepared to be weird. All right, so now that I've shown you a little bit about how combinatorial identities work, or at least proving combinatorial identities, I want to talk a little bit about what makes a good combinatorial identity, or what one might consider a good combinatorial identity. Because I don't want to tell you what you consider a good combinatorial identity. You may think they all suck, okay? And that's okay. I mean, you are entitled to your opinion. But at least try to imagine why somebody would think that some combinatorial identities were good. So you can imagine me or someone else who is interested in this nerdy stuff. So first of all, it should be an equation that we can use, that prove using counting methods. It's combinatorial after all, so we should be able to count in order to prove it. And the second thing is, when we look at the identity without thinking about the counting methods, it should be surprising. Right? When you looked at if you were to look at m times n equals m plus n choose 2 minus m choose 2 minus n choose 2, before I even mentioned sandwiches and salads, that is the craziest looking equation that could possibly imagine. You would think there is no way that equation is true. But we counted our sandwich salad pairs in both of them, so it has to be true. Right? So it's an equation that has to be true, but if you look at it without looking at the proof, you look at it and you say, there's no way that can be true. That's the best kind of combinatorial identity. So we counted the sandwich salad pairs in both, so it's a true equation, but it's a surprising equation if we don't think about how we counted it. And I just want to mention that for the combinatorial identity, we do not really care about the quantity we are counting. You may care a lot about sandwiches and salads, and that's okay, especially when you're hungry. But in terms of the combinatorial identity, we don't care about the quantity. We're just using the quantity to get our combinatorial identity. All right, so now I think you're worried. Now I think you're ready. Don't be worried. I think you're ready for the 2 sets of combinatorial proofs that I have ready for you. One of them is just called combinatorial proofs, and the other one is extremely creatively called more combinatorial proofs.